Let us consider in the complex plane an open set D and the functions defined on D, a function with complex values, D an open set. This means that for any point z0 of D, there exists a disk. We denote it, there exists a positive radius r such that the disk of radius r and center z0 is contained in D. We use the notation br z0 is the set of all the points z such that the distance between z and z0, that is the modulus of the difference, is less than r. This is the disk open disk, more exact, open disk. Let us also remark that if we add here an additional condition, 0 less than distance between z and z0, less than r, this additional condition exclude z0 from the disk. So this is the previous disk of center center z0 and radius r minus the center z0. For z equals z0, this inequality is not satisfied. That this is a disk without center. When we impose this additional condition. I shall remind you some definitions. We say that f, our function f defined on D to C is C differentiable at z0 if denoted by f prime of z0, the limit for z going to z0, f of z minus f of z0 over z minus z0 exists, and is finite. Z0, this is an open set, so Z0, our function f is defined around Z0 in a neighborhood of Z0. Particularly here we can consider the limit, this limit over any direction passing through Z0. C differentiable at Z0. We say that our function f from D to C is C differentiable without indicating the point, or also or holomorphic if it is C differentiable at any point from D. holomorphic or C-differentiable. Let us present two examples. A first example. The set D equals C minus 0. If we eliminate from C just one point, 0, this is also denoted by C star, is an open set, and F from D, from this C star to C, F of Z equals 1 over Z is holomorphic, is C differentiable or holomorphic function. Particularly here, the complex derivative at a point Z is minus, as in the similar to the real case, minus 1 over Z squared. You can obtain this directly by using the definition. For example, f prime at a fixed point z0 by definition is limit z going to z0 f of z minus f of z0 over z minus z0. In our case, limit for z going to z0 1 over z minus 1 over z0 over z minus z0. This is limit for z going to z0. Here we get z0 minus z over z0, z0 times 1 over z minus z0. We can simplify here and we get minus for z going to z0 minus 1 here minus 1 over z0 squared, and this for any z0. In this case, our function is defined on C star. This means C star is C, the complex plane, except we have to eliminate just the origin. This is evidently an open set. For each point, you can find a disk contained in C. It is sufficient to choose the distance less than the distance from Z0 up to the origin, the radius R. The distance, it is sufficient to choose this less than modulus of Z0 and positive. So it is an open set. A second example. For example, the set C minus I is open. And for example, the function f from D to C, f, we compose exponential function, for example, with 1 over z squared plus 1. This is a holomorphic function. Now, let us define the notion of isolated singular point of a function. A definition, an important definition. Let D be an open set, F from B to C be a holomorphic function. We say that a point Z0 which does not belong to D is C minus D is an isolated singular point, isolated singular point of F if there exists R greater than 0 such that Z here 0 less than Z minus Z0 less than R is contained in D. This is a disk without center. Disk without center. Our function is defined on an open set D, complex function, and but here are some points which does not belong to D, and they are isolated singular points if we can find such a disk without center. Z0, Z1, Z2 singular points, but in this case our function f is holomorphic in D, but it is not defined at Z0, but it is defined around Z0 where it is holomorphic. Example. For the function for f from C star to C, f of z equals 1 over z, the point z0 equals 0 is an isolated singular point. In this case, our function is defined on the complex plane C star, the C, except just one point is eliminated, 0, and our function evidently in this case you can find R an arbitrary for any positive R. This set, a disk except without the center, is contained in the domain of definition. For the second example, we consider f defined on C minus I f of z exponential of 1 over z squared plus 1. These 2 points I and minus I. In this case, the domain of definition is the whole complex plane except these 2 points. Evidently, it is an open set. For each point, you can find the disk contained in this set. These points are singular and isolated. Our function is holomorphic functions defined around each of them. Now we present a very important result. In the case of an isolated singular point, in the neighborhood of the point, our function can be expanded into a Laurent series uniquely determined, which is convergent around the point. Let us proposition. Let again D be an open set and F defined on D plus C will be a holomorphic function. If Z0 is an isolated singular point, then there exists R greater than 0 and a uniquely determined Laurent series such that f of z is exactly the sum of the considered Laurent series, sum for n from minus infinity to infinity, the coefficient a n z minus z0 to n. This for any z such that zero, the distance between z0, in such a disk without the center. Here is an isolated singular point, z0, which does not belong to D. Z0 is an isolated, we know that Z0 here does not belong to D, our function. Explicitly, this more explicitly, this formula f is the sum of a convergent Laurent series f of z equals a minus 3 z minus z0 third power plus a minus 2 z minus z0 squared plus a minus 1 over z minus z0 plus a0 plus a1 z minus z0 plus a2 z minus z0 squared plus so on, written more explicitly. In this formula, this coefficient is very important. The coefficient a minus 1 from this expansion is called the residue of f at the point z0 And we use the notation and denote it residue at point z0 of f. By definition, it is a minus 1 from the considered expansion. These residues of f at the isolated singular points play a very important in the computation, in the integration of f along certain closed paths. In the case when the Laurent series contains a finite number of negative terms, then we have a pole. Let us give the following definition. We say that Z0 is a zero of order k of f z if f of z0 is 0 as well as the first derivative, second derivative, all up to the derivative of order k minus 1. All are 0, but the next derivative, f derivative of order k of f at point z0 is different from 0. Now we say that z0 is a pole of order k of f if z0 is a 0 of order k of the function 1 over f. Example. The isolated singular points of the function f, let us indicate the domain definition be c minus except 0 I minus I to c, the function f of z equals 1 over z cube, z squared plus 1 squared. The isolated singular points are z0 equals 0. This is a pole of order 3. z1. This is 0 for z equals I, a pole of order 2, and minus I, z2 minus I, also a pole of order 2. Explicitly, this is 1 over z cubed times z plus I squared times z minus I squared. Now, a very important result. it is possible to prove that around a pole of order k, the Laurent series has the following form proposition. Around of a pole Z0 of order k, F admits an expansion of the form f of z, pole of order k. The Laurent series starts with a minus k, z minus z0 to k, plus a minus k plus 1, z minus z0 to k minus 1, plus so on, plus a2 z minus z0 square, a minus 2 plus a minus 1, the most important of the coefficient, z minus z0 plus a0 plus a1 z. The expansion around a pole of order k, this is the residue. This is the residue at z0 of f, this coefficient. Let us analyze the case of a simple pole. Example, if z0 is a pole of order 1, a pole of order 1, a simple pole, then the expansion looks like this. F of z equals a minus 1 over z minus z0 plus a0 plus a1 z minus z0 plus so on. In this case, we can easily compute this. It is sufficient to multiply by z minus z0, and we get z minus z0 f of z equals a minus 1 plus a0 z minus z0 plus a1 z minus z0 square plus so on. And if we consider now the limit for z going to z0, limit, f is not defined at point z0, so we cannot consider in this expression z equals z0, but we can consider the limit f of z will be a minus 1 and plus 0 plus 0 plus so on. So in this case, the residue, in the case of a pole of order 1, residue at z0 of f can be computed in this way, is limit for z going to z0, z minus z0 times f of z is just this limit. In the case of pole of order 1. Now, in the case if z0 is a pole of order 2, then our expansion f of z start with a minus 2 z minus z0 square plus a minus 1, our very important coefficient, z minus z0 plus a0 plus a1 z minus z0 plus so on. In this case, we multiply by z minus z0 squared, and we get z minus z0 squared f of z equals a minus 2 plus a minus 1. But we get, okay, plus a minus 1 times z minus z0 plus a0, z minus z0 squared plus so on. Now here we consider the derivative with respect to z. So z minus z0 squared f of z. The derivative of this is the derivative of a constant is 0, so is a minus 1 plus here is 2 a0 z minus z0 plus so on, and from this if we can express this coefficient if we consider in this relation limit for z going to z0 from this expression z minus z0 squared f of z derivative the limit will be a minus 1 plus 0 plus 0 plus so on. So in this case we get the following formula: residue at the pole of order 2 the residue can be computed as limit for z going to z0 z minus z0 squared f of z derivative of this. By using the same method, we can find the formula for the residue at the pole of order k, residue at a pole of order k is residue z0 of f is 1 over k minus 1 factorial limit for z going to z0 z minus z0 to k f of z, the derivative of order k minus 1. We get this formula. In the case when the singular point, isolated singular point, is not a pole, in order to compute the residue, we have to obtain, if possible, directly the expansion. For example, remark for the function f from c star to c, f of z equals exponential 1 over z, the point z0 equals 0 is not a pole. The expansion in this case, f of z around z0, you know, is 1 plus will be 1 over z, 1 over 1 factorial plus 1 over z squared plus so on. So in this case, we have the expansion plus 1 over 1 over z squared plus 1 over 1 factorial 1 over z plus 1 plus 0 z plus 0 z plus so on. In this case, this is the residue at point z0 of f computed by using directly the expansion. Now we stop here. Thank you.